Welcome student to example number 2, which is an example of the type all in all. In this example, we will recap and we will redo everything we did before. What do I mean by that? The question is find the interval where the following is increasing, decreasing, concave upward, downward, find all the local extrema, local maximum, local minimum, find the inflection point. As an extra, we need to sketch the graph of the function. So this is one of the most important application of calculus, that it helped me to sketch the graph of the function and know where is the increasing and decreasing, concave upward and downward, and find the inflection point. So this part, we will redo everything we did before. So it's a good review for whatever we did in the previous examples. So we start with this function. Of course, as first step, we need to find the critical numbers. Why do we need find the critical numbers? Because we need the critical numbers in order to find increasing, decreasing, and local maximum, local minimum are just critical numbers. How do we find the critical numbers? We just need to find the derivative, which is 5x power 4 minus 16x power 3, which is, if we just keep it as this, next step, we need to find the critical numbers. And remember, in order to find the critical numbers, it is either the first derivative does not exist, it has a problem, which is not the case here because this is not happening. Why this is not happening? Because there is no denominator. The second case is we have the derivative, or the first derivative, equal to 0, which means we have 5x power 4 minus 16x power 3 equal to 0, which means x3, 5x minus 16 equal to 0. The next step, we have two options for this one. Either x cubed equal to 0, which means x is equal to 0. The second option is 5x minus 16 equal to 0, which means x equals 16 over 5. We have those two options as candidate for the critical numbers. Next step, we find the interval where the function increasing and decreasing. Now, in order to do that, let me just write the derivative one more time, which is 5x power 4 minus 16x power 3. Next step, you do the number line. And in the number line, you need to find the sign of the first derivative. Now, what do we write in the number line? We write all the critical numbers. We have two of them. We have 0 and we have 16 over 5. Remember, 16 over 5 is, we need to find the approximate value of it, which will be just 3 over 3.2. Now, pick a number less than 0 and substitute it here. So what I will do, I will pick -1, and if we do that, this will be just positive, which means the function increasing. Next, take a number between 0 and 3.2. I will choose x equal to 1. Plug 1 here, plug 1 here. Everything in the middle will be negative, which means the function clearly is going down. So first thing we notice is the function goes up and down, so we have a local maximum at 0. Let's continue. Choose a number which is greater than 3.2. I will choose 4. If you choose 4, it will be also positive, which means the function will go up again. Now, things are much easier for us. Why? Because we can write the summary here. So where the function is increasing, the interval of increasing is actually from -infinity to 0. And then we start again from 16/5 to infinity, and we join them with a union. We have decreasing, which just between 0 and 16/5. Local maximum point, which is, remember, local maximum and local minimum will be at 0, and then you need to find, this is the value for x, and now you need to find the value for y, which is again 0. Finally, local minimum. Now for the local minimum, you need just to find the value for x, and the value for x is 16/5. Why 16/5? Because look, it goes down and then we go up again. And we need to find the value for the y, so we substitute here 16.5 and we will get the answer. The answer will be approximately -83.88. This is the value for y. So we find increasing, we find decreasing, we find local max and local min. Why do I need these? Because I will sketch the graph, so I need to know where to put this one and where to put this one. So when I sketch the graph, I can get kind of an accurate sketch for it. Next is we need to find concave upward, downward inflection points. So we find the intervals of concave upward, downward, and the inflection points. Now, what will be, how do we find it? We need to go ahead and deal with the second derivative. So the second derivative will be, now this is the first derivative. Now, how do we find the second derivative? Take 4 down here. It will be 20x cubed minus 48x cubed. So 24x cubed minus 48x squared. What do we need to do with the second derivative? We have two options for it. Either the second derivative does not exist, which is not happening here because we don't have a denominator or any problem with this function. Does not exist. And this is not happening. The reason why is because we don't have no denominator. Now the second case which will happen is the second derivative is equal to 0, which means 24x power 3 minus 48x squared equal to 0. Now if we take 24 as common factor, we get 24x squared as common factor would be better. We get x minus 2 equal to 0, which means either x equal to 0 or x equal to 2. And these are the candidates for the inflection point, concave upward and downward. Next step, we need to do the number line once again. We write 0 and we write 2. However, here we need to find the sign of f double prime of x. Not just f prime, it's double prime. So let's pick a number. Pick for me a number less than 0, which is, for example, -1, and substitute it here. So you will get just everything here will be negative, 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 which means concave downward, going down here. Next, take a number between 0 and 2. I will pick 1. The answer will be again negative all the way, which means I don't have inflection at 0. It will remain negative. Finally, take a number which is greater than 2. For example, you can pick just 3. And if you do it, you get positive at the end here. Which means this is concave upward going up. So we just need to write the summary that we have. Concave upward. It happened only once, which is starting from 2 going to infinity. Concave downward. It happened from negative infinity to 0, and then again from 0 to 2. Finally, inflection point, which means you have a value of course, inflection point is x equal to 2, and then we need to find the value for the y, the original function. We substitute x equal to 2. Let me go back to the original function and substitute 2 here and 2 here. Whatever we get is the inflection point. And it's negative 32. So we have all those information. Now we will use them to find the graph of the function. Now, before we find the graph of the function, there is one step. If we can do it, it will help us even more, as we need to find the y-intercept. And you remember from pre-calculus how to find the y-intercept. We need to find y-intercept by writing x equal to 0 in the original function. So the original function was y equal x5 minus 4x3. So, x4. So if we plug in 0, what do we get? We get y equal to 0. So the y-intercept is 0, 0. 0 is the value for x. The other 0 is the value for the y. Next, we need to find y, the x-intercept. And how do you find x-intercept? Your y must be equal to 0. So remember, the original function was y equal x5 minus 4x4. Now, if you plug in y equal to 0, we get x5 minus 4x4 equal to 0. Take x4 as common factor, we get x minus 4 equal to 0, which means either x equal to 0 or x equal to 4. So the x-intercept is 0, 0, 0 for the x, and y would be 0, or 4 for the x, and if we plug in, we get 0 for dy. Now we take all those information, we put them in one graph, in one sketch as follows. So I'll sketch here as much as we can. Of course, this will not be a perfect one, so let's hope our graph will be the best we can. First step, start with the intercept. Plug in the intercept. So remember, 1, 2, 3, 4, 5, 6. First of all, remember we have the x-intercept. One of them is at 0, 0, the other one at 4, 0. I finished this. The y-intercept again at 0, 0. Next step, find for me the local maximum. Let's go back, find the local maximum. Where is the local maximum? Local maximum is at 0, 0. So what happened at 0, 0, the function will go up and then down. Okay. How it will go up and then will go down? It must go like this. Like this, and then like this. Next step, find the local minimum. And the local minimum is at 16 over 5, which is a 3.2, and negative 83.88. So we go 3.2, which is here, and then we'll go all the way to 83. Of course, this will be just a sketch. So what we will do is we will assume this is where it should be, and this will be like this. This is negative 83. Next, we write the inflection point, and I think this where we will finish it up. The inflection point is at 2 and negative 32. Let me do it with a different color. At 2 and negative 32, which is this one. Now, what happened at 2? It goes from downward to upward, so it will be like a turn in the middle. So if I try to sketch it, I should go like this. I go like this, and then I change my behavior. So it should be like this. Going down, and then I go up. Of course, this is as much as we can. We just need to join things around. I don't need this. Okay, now this is the inflection point. Finally, this function will just go down because there is nothing I can join. However, here I need to continue, and I join it with the red one, and then I leave it to go up. This is the sketch of the function to the maximum that we can. So we need local maximum, local minimum. Now we go to part B of the same question, where we need to find all in all, which means we need to find increasing, decreasing, concave upward, downward, local maximum, local minimum, inflection point, and we sketch the graph. So this time we have a cubic function, and as the first step, as we just did, we need to find the critical numbers. Now, what is the critical numbers? It just, we need to find the derivative. So it will be 3x squared minus 12x plus 9. Now, since we need to look at two options for the derivative, either derivative equal to 0 or it does not exist. However, this is not happening. As you can see here, it's not happening because there is no denominator, no problem with the function. So we never get this one. So the only part we get is this one, which is the derivative equal to 0. Now, what we need to do is we write the derivative, which is equal to 0. So here we have two options. We get x equal to 1 and x equal to 3. Those are the two candidates for the critical numbers. Next step, let me just remind you what is the derivative. Next step, we do the number line, and we write those two numbers, which is 1 and 3. Now take a test point. So if you take, for example, 0, the first area would be just positive. Second area, if we take 2 and we substitute 2, it will be negative. And finally, if we take something greater than 3, it will be just positive. So what happened is the function increase and then decrease and then increase again. So if we summarize this one as increasing, we go from negative infinity to 1 and then from 3 to infinity, and we join those together. For decreasing, we start from 3 and we end up at from 1 and we end up at 3. For the local maximum, it will be just 1. And of course, we need to substitute at the original function by x equal to 1. So if we substitute by 1, what we get is 1, 1, 1. So what we'll get is 5. So here is 5. And local minimum, it will be starting at 3. And if we substitute here, what we will get is again, it will be y equal to 1. So we now found the local maximum, we found the local minimum, and I think now we're ready to go to the next derivative, which will be just 6x minus 12. 6x minus 12. Again, we have two options. One of them is the derivative does not exist, and that option is not for us because there is no denominator. So the only option is that 6x minus 12, which is the second derivative, equal to 0. And this means x is equal to 2. So we need to find the inflection point. All what we have is 2 here. Now, if we take a number which is less than 2, this area would be negative, negative, negative. Greater than 2, it will be positive. What does it mean, positive and negative? This means it is concave downward, and this is concave upward. So, where the function concave upward is from 2 to infinity, downward from negative infinity to 2, and finally, for the inflection point where the function changed from concave upward to downward is x equal to 2, and then we substitute in the original function, which is, if we go back to the original function, is this one here. We substitute every x by 2, so that we get, if we do it with the calculator, we get 15. So 2 and 15 is the inflection point. Next, we will need to find the y-intercept. Y-intercept means we plug in x equal to 0, so the answer would be just 1. So what we get is 0 and 1 is the y-intercept. For the x-intercept, we just find where the y equal to 0. So we need to solve this equation here. So you have x cubed minus 6x squared plus 9x plus 1 equal to 0. Of course, this is not an easy to be solved. So if you have a calculator, you can try to find the answers for it. Otherwise, as I just mentioned, is not something that we can find easily here. So we'll just ignore the x-intercept for now because it is not an easy thing to find the x-intercept for this question here. So finally, we reach to where we reach. First of all, if you remember what we just did, we need to claim the local maximum and local minimum, which is needed for us to join them as much as we can here. So what is the local maximum? is 1, 5 is local maximum, 3, 1 local minimum. So 1, 5 is local maximum. So it will be something going like this and going like this. And now 3 and 1 is the local minimum. So the function will just change into this. Now remember, at 2 and 15, just let me try to check if we really get 2 and 15. Oh, sorry, for the inflection point, I did a mistake here. This is not 2 and 15, this should be 2 and 3. We suspected from the graph, so 2 and 3 is the inflection point. So at 2 and 3, which is this point, the function has to go from concave downward to start going upward. And then all what you need is just carefully join them. Okay, good. Now we should erase what we can erase. And do the same thing here. All right. And now for the y-intercept, which is 0 and 1, so y-intercept will be this point here. I just need now to continue joining the function here, leave it go down, and this would go just up like this. And that's exactly